Yeah, so therefore they
Yeah.
should be on. Yeah, so welcome to, I think it's the 14th meetup for Papers to Love. So we have Eric Wanjau, who is a research intern at MSI, Microsoft Research, and is also a PhD student. So he'll take us through an image is worth 16 by 16 words. Yeah, so take it away, Eric.
Thank you, Rogers, and thank you, Nanda, for the invite. Yes, I don't know. I'm trying to put on slideshow. Yeah, fab. I hope my screen is on slideshow, and yeah. So yes, so my name is Eric. I'm a research intern at MSR Africa, and today we'll be talking about this paper, An Images World, 16 by 16 words, Transformers for Image Recognition at Scale. So please feel free if you have any questions to stop me or put them in the chat, and probably either Nanda or Rogers can bring them up. So yes, so yes, this is the paper we're talking about. So one of the heads up, this is a 2021 paper. Feels like a while ago now. Yes, so and this was one of the pioneering works to showcase how transformers first can be adapted to the computer vision research, and secondly, how they can altogether replace standard convolutions, which were kind of the state of the art back then for large image recognition. So at that time in 2021, convolution neural networks, sure, probably most folks here are familiar with them, had so far been the de facto for visual data. And yes, this was one of the first papers to show that vision transformers could achieve comparable or even superior performance on image classification tasks compared to CNNs at the time. And yes, so this is just a small kind of like snippet show how things evolved. We started with the original transformer for language, went to some known really state-of-the-art transformers for language such as GPT-3, and transformers came much a bit later, and vision transformers for that matter, the paper that we're going to talk about, and most of the research in vision transformers is based on this. So our idea was if we go through these papers, then you can have a good base knowledge of how vision transformers work and how subsequent works improved on them. So yes, so this is 2021, right? When CNNs were the factor models for visual data. So right now, in 2024, the success of transformers for computer vision is now really indisputable. We have transformers kind of have gained entry in most of research in computer vision. And you can see here Hugging Face transformers for various computer vision uh, uh, research. And you can here's a snippet from a paper Khan et al. That shows various papers in different computer vision problems. So this paper originally was for image classification, but from then other papers have other research areas such as object detection, image colorization have been using transformers. And like right now, transformers uh, can be considered as one of the go-to models in computer vision research. And just to a point, they have also gained entry as backbones for generative modeling. We've seen how generative models for text, such as GPT-3, Llama, have come a long way. Now we have generative models for vision, things like diffusion models, such as OpenAI Sora. Probably most people have seen these models, so you can put in a text and then it will generate an image or a video. So specifically for OpenAI Sora, the model behind this is known as the diffusion transformer. So diffusion transformers have really gained their footing in various research in computer vision. So yeah, that's it. A lot of hype on vision transformers. So let's see where let's take a step back and kind of look at how things how things progressed from the original transformer in text to vision transformers. So yeah, the NLP. Let's look at the NLP landscape back then, because if you read the paper, they're really trying to adapt with very little change to the original transformer. So I thought it was like good to have a background of this. So in 2017, the seminal paper "Attention is All You Need" by Vaswani et al. Was released by Google, and originally they set it up for image translation task, and then at that point, this outperformed recurrent neural networks and machine translation. And I'll just talk a bit about this. So, for anyone not familiar with RNNs, I wasn't really sure of the setting of our audience. So the RNNs are these neural networks that process input one sequence at a time, and then they maintain a hidden state that allows it to track information as it processes sequences at a time. So it processes a sequence, keeps a hidden information, passes it to the next to the next state as it processes the next input, and then combines that information, puts a hidden state, and so it puts a hidden state. It maintains a hidden state at each sequence it processes text, and in image, no, in translation, for instance, translating this text, it would transformers are great to something. I think this is German. So yeah, so it would process transformers are great sequentially, and in each sequence maintain a hidden state up to the last let's say token in the input, and that last hidden state. So this is the work of the encoder. So the encoder basically is it can be any neural network. You can see also the transformer architecture has an encoder and a decoder. So this is the encoder, is a decoder. So the encoder basically its work is to capture semantically meaning relationship of tokens in a sequence. So its work is just to see which different inputs in a sequence are similar to each other or are interesting to each other, and the decoder block takes that information and starts to generate text or translation. So the disadvantage of RNNs that time is the hidden state at the last token here, which is the exclamation, was expected to capture all this information, and then it can be used by the decoder to start translating. So at that time, RNNs were not really good at capturing long-range information. So that's why the transformer came in, and just let's just deal with this as an encoder and decoder. Will explain all this stuff in our talk today. But the transformer, what it allowed this mechanism called attention, whereby we didn't have to have one hidden state for the decoder to work on. The decoder can work on the hidden state at all sequences at all tokens in a sequence, so all elements in a sequences, and then it would combine that information in a meaningful way to get better translation. So that was the kind of the best selling point of the transformer. The attention mechanism allows it to look at all hidden states and combine the information among them in a meaningful way, in a data-driven way, to get better output, rather than the NRN, which was having just one state at a time. So yeah, so that was the NLP landscape. Something else was in parallel, there was this paper known as on Fit that showed that you can pre-train on a large corpus of data, and then you fine tune on smaller sub data sets. So this transfer learning, and like this is what has mainly driven the advances today in LLMs such as GPTs, Llama. You train on a large corpus of like internet data, and then you fine tune it on some really curated data set, and that's how you get things like like chatbots or something like ChatGPT. So that was the NLP landscape back then, the one that introduced the original transformer. So in the computer vision landscape, CNN's architecture that I hinted out earlier were the state of the art. So I want you to look past this. Once VITs came around 2020, 2021, they became state of the art, still up to now, but it was predominantly. So this is sorry. So this is kind of like the it's a benchmark data set. It's called ImageNet. Consists of a lot of images. Like I think it's the 1,000 classes. ImageNet. So before you could see like the convolutional neural networks, especially ResNet based, ResNext, ResNet, were the ones that were state of the art. And let's talk a bit about these ResNets. So they were based on this notion of convolution neural networks, or the convolution architecture, which are basically convolutions that basically filters. And the convolution operation is, as this example illustrates, is you have a filter, a learnable filter. So you don't specify in what the filter will do. So if you're familiar with image processing, like a filter is something like an edge detector or a horizontal light detector, or it can enhance certain features depending on the weights of the filter. So so the convolution layer you pass a filter over an image. So and then at each instance you do a dot product of the weights of the filter and the patch that it has processed. So you do a dot product, which is basically you do a multiplication of each element sequentially, and then you add them up, and then you get you get like a value that incorporates all the information in that patch. So that's how CNNs work. Probably this is folks know this, but this it allows you to go through an image at a patch at a time, and then you just slide it and do a dot product. And these are ResNets. So this an example of how ResNets look like. So basically, you stack all these convolutions. So stack all these filters which are learnable through backpropagation. And what will happen is that these filters will we learn values, or we learn weights that will allow them to extract interesting information from these local patches, and then it's processed and pass them to downwards filters down the line, which which will take those initially processed features and act on them and extract better representation of an image. So we stack them up, get a representation of an image that that tells us the most semantically useful features of the image, and then we can pass it through a fully connected layer and do some classification. So it's worth noting, long ago, stacking these convolutions it led to a problem known as vanishing gradients, because you are stacking a lot of filters, and they'll do a lot of transformation. Sometimes when you try and update their weights through something as back propagation, the derivatives of their loss with respect to this weight becomes really small, and this really inhibited training. So ResNets are known as residual nets because they do really one nice trick is that when you have an input, you can have like a shortcut layer, such that the input is passes unobstructed, and then you can have the convolutions here. So the output of a residual layer is you get the original input which has bypassed and the input that has been transformed. So the how this helps is, during backpropagation, when you're trying to update the loss, the derivative of the loss with respect to the weight, you an addition, if you remember your calculus, an addition allows you to distribute the weight. So the weights that were here become so I mean the derivatives that are here can automatically by like traverse through the network, and this prevents like if this was not here, the derivative would get would get transformed again by this layer, when it reaches here probably be too small. That's what vanishing gradient means. So but with this, the network can learn if these layers are not helpful, I can just distribute the gradient as it is. So that's the power of an addition in neural networks. It allows you to distribute the gradients that were here, and the gradient can pass unobstructed. And this really helped in training very large resonance. This was a really big breakthrough in computer vision. So yeah, so why was CNNs really good is that they have some inductive biases, and these biases, so inductive biases, they are like preconceived notions of how CNNs perform well. The first one is locality. As you can see here, they're able to operate on small regions of the image, and we know like in images, features like edges, textures often exist in small localized area, and the ability to do this automatically, CNNs is one of the reasons they performed really well. The 2D neighborhood structure, this patch is a 2D. This kernel allows it to operate on basically how the pixels are arranged. So it maintains the notion of the image automatically out of the box because of the 2D structure of the kernel still. And translation equivariant is because once you learn these weights, they can be able to detect, let's say cats. Cats are the most problematic. They can be able to detect cats, whether they are, facing horizontally upward. How cats are, or basically any feature in any location, because these weights of the kernel, they extract specific features such as edges, and once you learn those weights, you can detect an edge at any point. And these are the really inductive bias, which we'll come to later and compare them whether transformers have this. So yes, given that background of NLP and computer vision, the authors were inspired by the transformer scaling success in NLP, and they tried to experiment applying standard transformers directly to images with the fewest modifications possible. So this is the original transformer, and this is the vision transformer. And the vision transformer only uses the encoder of the original transformer, because you said encoder allows you to capture this semantic relationship between various sequences in a token, and then you can use that to do either a classification. They were doing a classification at this point. So in that previous work had shown that when increase in CNN performance, when you do transfer learning from large data sets. So the authors also explored how, they explored how transformers can work when pre-trained with large data sets, because as you said earlier, that's how the original transformers are pre-trained in the case of text. So they also experimented if we scale a transformer and you scale it in terms of data and its structure, can we get better performance? So these are the two objectives for this paper. So yes, the vision transformer, basically, when you think about it, it's relatively straightforward, because this is all they did, and will be. So this is a vision transformer, and they did this. They split an image into fixed site patches. They linearly embedded each of them. They had positional embeddings. Then they feed it into a standard transformer, and then they do classification. So yeah, so we'll be delving into hopefully every part of this transformer encoder, so that anyone who isn't familiar with a multi-head attention that I was talking about, we can go through it again. So yeah, so let's go. Let's split. Split. So let's go through each of these steps one at a time. So the first step, we said, is they split the image into fixed size patches. So let's see how. So the standard transformer, this is how it's done in images. So the standard transformer, the one for text, I think I'll be saying transformer is text, and then vision transformer is for vision. So the standard transformer, the text one, receives a 1D sequence of token embeddings. So what this means is, text is by nature a 1D sequence. Like, transformers are great, but visions are 2D or even 3D. So so let's see. So for text, you say something like transformers is great. So this word is first tokenized, and tokenized just means you represent the word from actual text to numbers that can numbers in a large dictionary that you can represent the text in, and then after that you project these numbers into an embedding. So this word is usually overly used, but embedding is just a vector of random numbers at first. So for instance, so this vector is usually something like 512 dimension, but here we just consider 5 dimensions. So here when you tokenize, you get 5 tokens, and then you project them into these random sequences of numbers which are learnable, and they'll be updated during backpropagation. And yeah, so this is what you feed. So these numbers allow the transformer to find interesting relationships between to represent a word in an interesting way, such that other tokens can understand it. So that's usually the how for text works. So to handle 2D images, we just need to find a way of getting a 2D image and flattening it, basically, so that it can look something like this. And that's what we are going to be discussing, how it happens. So in the paper, I'll be taking excerpts from the paper, and then we'll be going through them. I thought it would be easier. So here, the standard transformer receives, we've said that. So that's what we're trying to do in the end. So it's good to have the goal in mind. So to handle 2D images, we reshape an image X, which belongs to a set of real numbers, height times width times channel. So this just what this means is X is an image, and it belongs to a set of real numbers, and it's height times width times channels. For instance, RGB image, that's what they'll be dealing with. So we want to reshape this into a sequence of flattened 2D patches, where a patch is also a real number of dimension n times p squared c, where HW is the resolution of the image and c is the number of channels. We'll go through this step by step. So let's first switch there. So you have an RGB image. So in the regional transformer, they use 224 by 224 by 3. So 224 height, 224 width, and then 3 channels, 3 color channels. So the first step is, how do we reshape this into into patches, because our goal is to split an image first into patches and then we flatten them. So we've been given a formula for calculating the number of patches. So for a 224 by 224 by 3 images and a patch size of 16, the title of the paper was an image was 16 by 16 words. So we use 16 pixels. So when we have, so the number of patches that from a 224 by 224 image is basically you take the width and you take the height and then divide by the number of patches that you're dividing into. So 224 by 224 over 16 by 16 is basically you get 14 patches you get 14 patches height and 14 patches on the width, right? So yeah, we are getting somewhere. So we are somewhere here. We have been able to calculate the number of patches. So that's the first step. We've taken an image and we've split it into patches of 16 by 16 pixels. So the other thing to do to get a flattened vector is now to flatten it. So for instance, here we have patch 1, right? So it's 16 by 16, but remember it has 3 channels, right? So how do we flatten that? And we flatten that by doing how do we flatten that into individual let's say individual pixel values. So basically it's the total number of pixels here is 16 by 16 and then times the 3 channels. So that's why it's p squared c. And yeah, basically when you have this, you can flatten it out. So this is a hypothetical. This is the first patch, and then we flattened it out. Then we've taken the second patch and then flatten it. How do we flatten it out? We flatten it out by taking P times C. So basically, when we flatten things out, you go from these 14 by 14 patches across 3 dimensions, and then you flatten them out to single patches. So in terms of the vision transformer, we get 196 patches, and the flattened length of the pixels will be 768 because it's 16 times 16 times 3, so that's 768. So when we flatten things out, we get 196 patches, right? 196 patches, all these 196 patches that flattened out into a dimension of 768. So yes, so basically we are here. So to handle imaging, we reshape the image, which was this, into 2D patches, which are a set of real numbers of dimension n. So n for this 196 patches and dimension p squared 16 times 16 times 3. So we flatten them. And yeah, so we're done. We're getting there. So the transformer uses a constant latent vector d through all its layers. So we flatten the patches and map to d dimensions with a trainable linear projection. So let's take this law. So we already have our patches, right? We already have our patches, which are 768 dimension. And as I said, the regional transformer is let me just take you back. Is you remember this? We have to probably we are here. So we have to go from this to for images to get like like an embedding, so a d-dimensional vector of all the patches. So how do we get here? And here we are being told because the transformer uses a latent vector size d, so we have to transform. We have to reproject our patches so that each patch has a d dimension. This d dimension can be anything, so it can be 768, can be 512. These are the ones that are typically used, and we do this using a trainable linear projection. So how does this go? So we take this 196 patches times 768, which we have flattened, and then we give them to linear layer. So if you're familiar with Python, this is just nn.linear. And basically what this does behind the scenes, it takes these patches, 178 and 768, and then multiplies it with a learnable weight, and then you add a bias. So this is just a linear equation, y is equals mx plus, is something like that. So this is the patches, you multiply by a learnable weight, which you transpose, and then you add a bias. And this weight is of dimension d, and that d is the so d is the width dimension you want. So probably the width in this paper they used if you go to, I think, table 1, they used a d dimension of 768. I think they used different for different variants of the transformer. So this weight will be of dimension d and p squared dot c. So we'll see why that should work. So for instance, this d is 768 for this type of transformer. For this type of this is a Vit base for this type of vision transformer base. So we have our 196 times 768 patches, and then we're trying to get a linear projection. So we're trying to project it to the dimension 768 of the transformer. So we multiply it by a vector d times 768. So like this has to be like this, so that when you transpose, it will be 196 times 768 multiplied by 768 times d, and that will so the matrix multiplication will work, and then basically we'll get 196 times d dimension, and d is the dimension of the vit we want to work with, and this was still 768, just like the p squared c. So yeah, so then thing to notice, this is learnable, and then you add a bias of the same dimension 768, so that things can work. So that it allows the training to be not very rigid, to like move about with how the data looks like. And yes, so that's how you basically transform a 196 times 768 flattened representation to one that the transformer can accept. So yes, so I don't know if you have any questions here, but so this is basically what we've done is we've taken an image, we've split it, we've flattened it into n times p squared c, where p is the part size, and then we've projected it using a learnable linear projection to now this is known as like a patch embedding, it is in a way that now the transformer can start processing. So this is this is represented in equation 1. So I know this looks like some very evil looking math, but basically what we've done, forget about x class e position, is we've taken a patch, and then we have multiplied it by the trainable linear projection. As you can see, theirs is basically the same as ours. Ours, we've just transposed it, but this will still work. So, and the reason for doing that, we are trying to reproject it into the dimension that the transformer wants. So yeah, so right now we know what this means. So it's a patch, and then matrix multiplication by the embedding dimension. So you know what this is, and we do this for all these patches. So what does x class mean? What does e position mean? So we'll be going there in a bit. So basically, this just us like going through what we've done. We've split an image, we've flattened it, we've projected it in a linear projection, and then we can get kind of like the embeddings of all the patches. So what we've done is, so we are basically somewhere here. We have a linear projection of flattened patches. So we need to add two more things. We need to add a patch and a position embedding. And I'll explain what those mean in a few. So so let's add the the extra class embedding. So if you remember, we are trying to adapt the original transformer into a VIT, and the one of the before LLMs, one of the like large transformers for not large like LLMs, but one of like the major transformers for text was known as BAT, and BAT had like a class token that was prepended at the beginning of the sequence, and the function of this class token, it was a learnable token, and it basically its work was to summarize all the information from all other tokens, so that it serves like an aggregated something that has all the information that represent the whole sequence in just one like one dimension, and then that can be used for things like classification. So the others also do this for the vision transformers. So they append a learnable class embedding at the beginning of the rest of the embeddings, and this is also serve the same purpose, is to collect information from all other patches, and this information will most likely represent the most important features of the image in the final layer. And then after that, they would add a multi-layer perceptron. So multi-layer perceptron is just like the learnable projection we've just discussed a few seconds ago. And this will map from the dimension of the transformer to the number of classes. So for instance, if, as we said, we have a 196 and 768 embedding. Once it goes with the MLP, it will be something like 196 or 197 patches, as we'll see, and then to like 1,000 dimension for, and each is a that we calculated. And this the dimension recovered by the transformer, and here it is 768. So we we prepared this extra class embedding. So here, this was the original, so we just prepared an extra class embedding on top, which is here, and then this becomes 197 times D. So this just basically means this token will be responsible for figuring out all the important information from all other patches, such that we can get like a compressed like a compressed rich feature representation from all other tokens. So yes, so basically now now we know from the equation one that what X class is. X class is this extra special embedding that we are putting on top of or at the beginning of all our patch embeddings. And yeah, we already discussed this, and then now we still don't know what position embedding is. But yeah, this text also represented equation 4, and this is the Y is a layer normalization of the last it's a layer normalization of the last how do you put of the last matrix produced by the transformer. So you don't need to worry about that for now. So yes, so where are we so far? We've flattened, we've put it in, we've linearly projected it into the dimension of the transformer, and then we've added an extra patch embedding. So there's still the position embedding a bit. So yeah, so this requires some previous prior knowledge of how attention works, which we'll still go through in a bit. But in attention, as you probably hinted out earlier, attention allows a neural network to look at all patches, at all patches, and then aggregate information from all patches in the sequence in a semantically meaningful manner. So when we flatten like this, and the transformer for each patch, it's looking at all these other patches. It needs it needs a notion of the position it's in. For instance, I'm patch number 1 and I'm looking at an eye, and I think the ear will be more interesting to me. So it needs to know like the position of itself and all the other flattened patches, in relation to it. And this is where, like, if you remember the CNNs, they would maintain this, structure automatically because they would just slide, a kernel, sequential, and they'll retain the notion of the of position, but a transformer and attention doesn't allow this. So we need to add we need to add another learnable. So here they used another learnable embedding. So it's just a vector the same size. You see the same size as our projection of the flattened patches, and this learnable, which is start at random, it will tell the position of each flattened patch. So what am I saying is that we have the original the original embedding of the original projected embedding of the image patches. This is the patch 1, patch 2, patch 3, and it's flattened. And we have 197 because, sorry, this is the extra class token that will aggregate all the information. So we need another position embedding, so another random vector start, which is learnable. And it will also have the same dimensions that it can tell, like this patch, this is your position, this is your position, this is your position, this is your position in the original image. So yeah, so that's the notion of adding position embedding. So we will have an updated linear projection of patches of the same dimension, because you're adding 197 times d plus 197 times d basically. So we get an updated projection that now has the notion of the position of each flattened patch. So yes, so now we know how this initially looking evil equation, what it means. We prepare an extra class embedding, we project all the patches into the embedding shape of the transformer dimension, and then after that we add a position embedding, and the position embedding should be basically n+1, because we prepended an extra token times the dimension of the transformer expects. So yes, so we are nearly there. If you look at it, so we've added this, and now it's basically it's just plugging it into the transformer encoder, and that's the last bit. So the transformer encoder consists of alternating layers of multi-head self-attention with touch in a bit and MLP blocks and layer normalization. So basically we have our flattened embedded patches now, which also have the notion of position. And yeah, we pass them through layer normalization, a multi-head attention, layer normalization, multi-head attention. Then we have these skip connections, which you remember. So basically, we've covered all the equations of that were in this paper. So you have this equation. Then this means we'll do a layer normalization. So this is here. So a layer normalization of the previous layer. So what this this encoders, this transformer encoders, you can see it's LX. So we stack them up. So for instance, we'll stack 12 up, I think, for this paper. We'll see in a bit. So they stacked 12 up, and so this means you'll do like a layer normalization. Have the embedded patches. First to do a layer normalization, which is this of the previous one. And then you do multi-head self-attention, which I'll just talk about it in a bit, and then you add the skip connection, which, as I said, allows gradients to traverse through and prevents like the gradients of the loss with respect to the parameters from becoming very small. So yes, so and then we have again we have another layer normalization. Yeah, and basically the work of the layer normalization, it allows this intermediate representation to be like to follow something like Gaussian distribution, because you standardize them. You take for instance the you take, like, for instance, this, and then you minus the mean and you divide by the standard deviation, and then you have some learnable like shift and scale. So it allows you just to put them in you're allowing the model not to care so much about, or to become like invariant to huge changes in the distribution of these intermediate steps, and concentrate on learning. So it helps in model learning, and it helps in model training, and keeping these intermediate activations in a really nice distribution. But it has a learnable scale and shift, so that this can also change with how the data in a given patch is. So yes, basically, if we're not going through the multi self-attention we've done, we've actually like covered most parts of the paper. We start with an image, we flatten it, we split it into patches, we flatten it, we project it into the dimension of the transformer. We have added a patch and a position embedding, and then we are putting it through a transformer, and it will go like layers of normalization, multi self-attention. So yes, I thought it would be also wise to go through this in case anyone wasn't familiar with the original transformer, and because with this, the notion of attention and self-attention, multi-attention, attention, doesn't change in the vision transformer and in the original text transformer. And this was like one of the beauties of the transformer architecture. Like, it allowed us to have this one great algorithm, and we just have to like make our inputs, either their images or or text or audio, to just a form that the transformer can process, and the rest is the same. Very few things have changed, in fact, for yeah, in the original transformer. Just updates in terms of efficiency and and it representing things better, like the position embeddings, but few things have changed. So that's really one of the advantages of the transformer, and how it's become so like predominant in kind of like all domains, kind of like unified domains. Like, now you can protect, you can process texts, this multimodal model, text, audio, and and images, and using videos, using the transformer, the same architecture. So yes, so what's attention? What's self-attention? All this. So as I hinted earlier, attention is a mechanism that allows neural networks to assign a different amount of weight to each element in a sequence. So it looks at all elements in a sequence. Here you can think of patches or even text. I'll say tokens for patches, but yeah, so you look at all like tokens in a sequence, and then the attention mechanism allows the neural network or the transformer to assign different weights of different attention to elements that it find interesting to it. So the trick is this. So instead of using a fixed embedding, such as like this fixed embedding that we have calculated, that has the position, that has the learnable parameter. So this is fixed. Instead of using these fixed embeddings, we allow the tokens or the patches to look at each other. So this is very loose language. So they allow the tokens to look at each other, and then find other tokens or other patches that are interesting to it, and then update the information by linearly combining all the information from all other tokens in the sequence. So we don't use a fixed we don't use a fixed flattened embedded patches or a fixed token. We take that, but self-attention allows each token to look at all other tokens and then update its information. And this is the information, this is the dimension of the information that each token has. It allows it to update it by and incorporate the information from other tokens in the sequence. So how does this? Let's see how this happens. So let's have a look at this image here. So let's see how attention, like how it allows us to get the context of the word flies in different contexts. So time flies like an arrow. So this is the notion. So this was the this was the fixed embedding for time, this was the fixed embedding for flies, fixed embedding for light, fixed embedding for ant, fixed embedding for arrow. But with self-attention allows each token to look at all other tokens and then combine the information from other tokens to get some better context. So when this token, it updates its information. Remember, it was blue, but now it has all different colors. And then with that, the that the neural network will know that this flies means like to fly, like to soar. Still, in another example, fruit flies like a banana. These are the original embeddings of each word, but instead of using a fixed embedding, self-attention allows each embedding to update its information based on the information from all the tokens in different proportions. This is shown in different proportions. Probably flies took more information from banana than or banana and fruit. So in different proportions for other tokens, and then get the context. So yes, so that's the notion of attention. That's what allows us to do, and that's how it can work in both text and patches. So how do we compute this contextualized embedding? Calling it contextual embedding because they've captured information from other sequences, so they have context. So basically, attention is usually this just scale.product attention, to be precise, the one used in the transformer in VITs, is usually just this set of small equations. See, it's not like some really complicated concept. We have softmax, we'll explain what that is, we have query and a key and a value, and then we scale it. So it's just this really simple and neat trick. So yeah, so this is just showing it's really it's a really simple and neat trick that we're going to be going through. Sorry. So okay, I'll introduce this. I want to introduce this stuff, but let me introduce this now. So we have this is the attention scale.product attention, but if we do it many times, if we do it many times and then we concatenate everything, we'll have attention from various we'll have how do you put it, we'll have context, we'll have different contexts, because that's what we call attention. So we'll have very many different contexts, and when we combine them, we can have better understanding of the sequence. So in the because in the VITs we used to see multi-head attention, so that's attention that has been repeated many times, so that we can get a better general understanding of all the patches in a sequence. So let's learn a bit about this. How does scaled dot attention work? So the first step, so it basically has 4 steps: this, scale, softmax, and this. So 4 easy steps. So the first step is to project each token embedding into three vectors: a query, a key, and a value, and each will have a dimension d, which is the hidden size of what the transformer dimension the transformer want over the heads. So let me explain this in a bit. Probably can be a bit confusing. So we're working with VIT base, which has 12 layers, 12 stacked layers, and it wants an input dimension of 768. So basically, that's what we're saying, 196 patches, each of 768 dimension. I mean, 197, each of 768 dimension, and it has 12 heads. So it has 12, 12, 12 attention, 12 attention like functions. So as you said, multi-head attention is we do it many times and then we concatenate. So we want each attention to produce a dimension 768 over 12, so that when we bring them all together, they can be equal to the original hidden size. So that's what basically this means. So for instance, 768 over 12, this is 60, this is 64. Yeah, so we remember the original. So let's show this. So we remember our original flattened embedded patches, which were 197 times D, and this D768. So we want to project it into three vectors, a query, a key, and a value. And this projection is also learnable. We do it using a linear layer. So what does this key query value mean? So a query is, in layman's language, is this is what I'm looking for. So this is a patch. We have 196 patches, and this 196, all these 196 patches, they emit a query. So this patch have covered an eye. I'm looking for the other eye of the cat. I'm a patch of the knee, and I'm looking for the whole foot. So that's the notion of query. So we take all these 196 patches, and then we tell them emit what you want, and that's the first. So that's the first step. So it uses a trainable linear projection to emit a query, and to emit a key, to also use another randomly initialized key projection, another value, another randomly initialized trainable projection. So we covered this a bit earlier. So this is the original flattened embedded patches, which is 197 because of this extra Lambo token and the D dimension 768. And then we want to transform it into 768 over 12, so that when we can combine them, all of them, we'll have the original dimension D. So we have 110 times 68, and then we want to do to project it, to use this linear projection, which is just basically we multiply and then we add a bias, and we multiply with a learnable weight, which has a D times D dimension, so that things can work out. So basically we have 110 times 768, and then we want to do a matrix multiplication with another matrix, which is D is 768 over 12. And then we'll have to transport it for the matrix multiplication to work. So 197 times 768, and then this is the D we want to project it into, times 768. So when we transpose this and this will match, so we'll get a 197 times 64 query. And this is a query that's asking, this one not said in the original. This is just an intuition. This is each of these patches, like projecting what it's looking for, and we get in the end all the 197 patch, and then the query information. So the same thing happens to this again. The flattened patch embedding emits a key. So a key is saying that each patch is saying this is what I have to offer. So you're looking for an eye. Are you looking for another eye? Yes, I think I have the other eye of the cat. So again, the all these flattened embedded patches, what they do, they emit a key, basically in response to the query. This is what I have, and the embedding of the key is the same as the query. They have to be the same. So which is D over heads, and basically this is just 64. So they emit a key in response to the query. And then lastly, the flattened embedded patches, they also emit another projection known as value, and value, this is the information that I will give you if you find my key interesting. So if I have the response to your key, then I'll give you this information, and then you can combine it in a smart way, and then you'll update your information. So that and it does this, using another trainable linear projection. They start at random and then they get updated during training. So when you think about this, is to get a query, a key, and a value, you use different trainable linear projections and different weight matrices. So if you do this many times, you get many queries. So you ask many questions, you have different responses. That means you'll have more information at the end. So that's the first step. So the flattened and embedded patches, they emit a query. This is what I'm looking for, a key. This is what I have, a value. This is the information I'll give you if you find me interesting. So yeah, that's the first thing. That's the first step of self-attention, and it's called self-attention because this key, query, and value are emitted by the same flattened patches. So you'll find in other things such as translation, the query is emitted by one language and the key is from another language. But this, because all these are from one set, that's why it's called self-attention. So once we have emitted a query, a key, and a value, now it's finding my query and my key, how interesting are they, so that I can know what information to take from. So the next step is to determine the query and the key vectors, how they relate to each other. And this is done using, a dot product mathematically, and it's easily done using matrix multiplication. So we have a query and we have a key, right? So remember, we emitted a query, which is n plus 1, basically, but n times d, and a key, which is n times d. So for the math to math, we have to transpose such that we have n times d times n, so that the inner matrices can match, and then we'll get an n by n sequence. So in our example, we had this query, right, which was an n plus 1 times d. Then we have transposed the key, and then basically we get an n by n, an n by n kind of like embedding. So this will be a 197 times 197. So just to point out, when you hear people say that transformers are quadratic in in the performance, it's because of they'll first result in an n by n matrix. So imagine if this was 10,000, this would be 10,000 by 10,000. That's too long. That's a very long context length. So it's quadratic in it. That's one of the kind of like the limitations of transformers, and people are trying to see how to play around with that. But for now, yeah, this will result into an n by n how do you call it, matrix. But something I want everyone to take from this is, once you have a query and a key, and you find how they are related to each other, you have something like this. So you have something like that tells you this token finds probably the query of this token and the key of this token are they are very similar. They find each other interesting. For this ones, they don't find each other interesting. Probably for the last one, they don't at all find each other interesting. So this is kind of like a similarity of how interesting the query and the key are to each other. So that's why you have faded colors and all. So it's, when you see, and this will make sense just a bit, because after we've computed how each query and key find each other similar, the next step is to do the attention weight. So we are here, we have seen how the query and the key are interesting to each other. So the other part is to compute the attention weight, and the attention weight is, these dot products, this query times key, they result in very large numbers, which can destabilize training. And that's why we normalize by the dimension of the query or the key, so that we can reduce the variance. So the variance is usually additive. So once you have the query and the key, the information will be very much away from the mean. So that's why we kind of normalize it by doing square root of the variance to prevent them from being too large. So, and then to better interpret the attention score, which computed areas the query times key, we apply a softmax. So basically, a softmax is it's an exponential function that converts like k that converts it to components, that converts its elements into a probability distribution that sums to 1. So what this means is once we've normalized, we apply a softmax, and then this means that each of these attention weights that we've calculated, we first had our attention scores, and then we've normalized, and then when we do a softmax, this will result in a probability of how interesting each query and key find each other. So for instance, we say like this the second so like this patch finds the second patch really or more interesting than all the patches. So it's kind of like a probability distribution of how, which sums to 1 basically, of how each patch finds all the patches in the sequence interesting. And this will allow you to take the amount of information you want from the rest of the other patches. So which you'll see in just a bit. So the last step is after we calculate the query and the key, and then we have done a softmax, which tells us the probability of how each token of each patch find each other interesting. We then update the information. We then update our information, which using the value key, and the value, using the value projection, and the value is just, and when you do, by doing a matrix multiplication, and this allows the, the original embedding to add information in different proportion to itself. So it allows us to contextualize all other tokens or other patches in our sequence. So we have an n times n, which we got as the attention weight, and then we'll have a matrix multiplication by n times d. Remember, this was the original value dimension, and then we'll end up with an n times d vector. And the good thing is, these are the attention weights. So if we do matrix multiplication of, so this is the first patch, and the first patch, these are the probabilities that it finds all the other patches. This is the amount of information it wants from all the other patches. So if we do a matrix multiplication of this and this, basically get a single value that has aggregated we said value is the amount of information I'll give you. So has aggregated the values from all the other tokens in different proportions, because you remember these are probabilities that sum to 1. So probably it will have a higher, it want more information from this, less information from this, different proportion, then add them up when you do matrix multiplication, then you have one representation that has all the information from all the tokens. And yes, so this is attention for a single head. So everything that we've done up to now, all this is one instance of attention. So if we do it many times, if we do it many times, that means you'll have different queries, different keys, different values. With different queries, we'll have different queries, different things that each patch wants, different responses and different information. And when you concatenate all of them together, we have a rich contextualized embedding that has combined all the information from other tokens in different ways and in different proportions. And that is known as basically multi-head attention. It's just a single attention head repeated many times using different projection of keys, queries, and values, and allows it to combine information in different proportions and different ways. So yeah, that's it for vision transformers. We've gone from a 2D image, we split it into fixed patches. We've projected them to the dimension the transformer wants. We've added a patch and a position embedding, and then we've known how we've done normalization. We don't know how multi-heads of attention works. It's just basically each token looking at all other tokens and then combining information from them in different proportions. And then we add this keep connection because they allow gradients to flow easily during back propagation, so they don't get diminished. And then we do another normalization to make sure like these these internal representations are in a good distribution. Ideally, a Gaussian distribution has been shown to work well, but it's scaled and shifted depending on learnable parameters. And then we have an MLP, which is basically, as we saw, MLP is just a trainable projection that's just y is equals to mx plus c. And this allows, when we are doing all this multi-head detention, we're looking at all other tokens. But when you do matrix multiplication, like when you do a row times a column, it's basically each patch now having all the rich information from all other tokens allows it now to kind of like think on its own, like, okay, so I have all the information. How do I update my class embedding to contain all the information? This is where kind of like the thinking happens in the MLP because it happens individually for each token. And then this is combined, put in another multi-layer perceptron, and then does classification. So very fast, I'll go through the results. For this paper, they noticed two things. When trained on mid-sized datasets, such as the ImageNet for 1,000 classes, without strong regularization, the models yielded modest accuracies, even below CNNs. And then this is due to transformers lacking, these biases that we talked about CNN, such as translation equivariance and locality, because transformers don't have locality, they look at everything at once. So so for instance, this is the VT huge. So as you see, when it is trained on very large images, when it's pre-trained on very large image data sets, such as GF to 300 million, it beats ResNets basically at all metrics, at most of all the metrics. And also VIT large, which were really analyzing of size 16 of patch size 16, also beats ResNet on when pre-trained on very large data sets. But when it's pre-trained on smaller data sets, such as ImageNet 21K, so this ImageNet that has 21,000 classes, it basically performs a few points less than ResNet. And this is just to show that this is not surprising, because transformers, they lack these inductive biases on small data sets. But when you pre-train on very large data sets, large scale pre-training, it trumps down inductive bias, and the VITs approach or beat state-of-the-art ResNets. This is also another result you see on ImageNet. On the small ImageNet of 1,000 classes, VITs beat transformers. On the ImageNet of 21 classes also, it's a bit, but it beats bit means I don't know, I've forgotten, but these are just ResNets. It's big transfer learning. So the ResNets still perform better than transformers, but when we scale them up to large pre-training, the transformers beats the ResNets. So yes, so since then, I'm winding up. There have been many improvements to VITs to improve efficiency, design, incorporate 3D data, lower computation costs. Remember the N times N stuff, and also to do other things other than image classification, to do things like segmentation, and so this These are some of them. I'll have them in the references for everyone to look at them. But yeah, probably I want you to see this, like the date. It came after this. It allowed VITs to be trained without this very large data sets. They actually trained on the ImageNet, I think 1,000 classes, and they used a CNN teacher to train a VIT and allows it to not, so because you don't have access to some of these very large data sets. For instance, this JFT is usually internal to Google. So if we don't have it, how will we pre-train these VITs? So anyhow, these are some of the things that have happened. And also I want to point you to this, like masked autoencoders. So as you've seen, like this pre-training was supervised. It was supervised. Remember the MLP head for doing classification, but masked autoencoders, they allow the introduced a way of doing unsupervised learning, very similar to NLP. So you hide some patches and then you make the model predict what was the missing patches. Very similar to next token prediction that's very famous in NLP. But yeah, I'll leave this to references and further reading. And then if you want to get started, Hugging Face is the best place to do to learn about vision transformers in various computer vision like research and domains. You still have it for audio, you still have it for NLP. So and then they have really nice examples. If being more bullish to computer vision, they have a course, a really good computer vision course that goes through all the fundamentals of computer vision research. Yeah, one of my favorites is also Andre Kapathi, the GOAT. Has really nice tutorials that allow you to understand transformers and transformers and neural networks in general. And he also builds it from scratch. So really, really nice place when you want to get into AI and know how these neural networks learn and the intuition behind all this stuff. And yes, and also for transformers, this Pastor Neil Rog, he gives very nice transformer tutorials when they come out, for all these computer vision tasks, basically. So big shout out, and also like nice person to follow and look at his tutorials. There are thousands of them. So yeah, I think I'm ending that. So references, and thank you for attention. And and thank you for listening. And please, I'm welcoming any questions. Thank you.
Wow. Thanks so much, Eric. Yeah, we can clap, virtual claps. Yeah, I really loved the level of detail you went into, like doing this stuff, and I appreciate you walking us through. We went over time, but it was really interesting to to stop you or
Yeah.
interrupt you.
Sorry.
Yeah, but no, that's all good. It's all good. The good thing this is recorded, so for those who dropped, that people who left for like some other meetings, like Rogers left, they will catch up on the recording. But before we close, I could just open up for any questions. Anyone who's the folks who are still on the call for any questions or comments.
Hey, I have my hand raised, so I guess I'll go.
Oh yeah, sorry, you can go. Sorry, yeah, sorry. Go ahead.
Yeah, thanks, Eric. This is awesome. I now understand how multimodal models work. And
Wow.
this a quick follow-up on that. Does that mean like GPT-4 and its variants? Does that mean like they're basically a combination of different transformers?
Yeah, that's a good question. So my thinking is, you have yes, you have different transformers. So you have like um like a transformer for images, so like an image encoder. So you have like so that one will so you have an image encoder like the one we just used here. So takes an image and outputs a representation that has taken into account all other patches and has contextual information of all the patches in the sequence. So and then we have like a text decoder. A text decoder that will take text and then we have at the middle we have like a projection layer that will put the dimensions of the image and the text match with the text, and then you can do things like cross attention to to either generate like a description of the image or something like that, or answer something that was or answer a question based on the image. So it's a different transformers, but they have like this trainable projection at the middle that allows the image to kind of like be in the space of the text, and then after that it's just cross attentions between those two.
Cool. That is crazy. So it's not like a hidden. I thought they were separate, but like when they're trained, the outcome is actually just one model that can actually process images, text, and voice even these days. Okay, it's
Yes.
crazy what transformers can do.
So that was like the the benefit of like they have transformers have kind of like unified all. We used to have the image people with CNNs, text people with LSTMs, and then like now we are all using transformers and just different cross attentions. You play with the query and key to get information from the other domain.
Thank you. Crazy.
Bob. Thank you.
All right. Any other question? Yeah, go ahead, Tom.
Yeah, hello.
Yeah, hello, Tom.
So I recently learned that in self-driving, they
Yep.
they still prefer using CNNs compared to using VITs. So why is that so?
Not getting into any politics, but that was a claim made by LeCun, like also like the one of the godfathers of AI, that like CNNs are faster than than transformers and all. But actually, if you know a company called Comma AI, it's also trying to it's a big player and also in the self-driving cars. Like they refuted that claim, and they actually use transformers in self-driving cars. So I would say it's now like with the efficiencies in transformer architecture, like there are advancements in calculating, in reducing that quadratic n by n matrix and other ways of making it faster in subsequent research. So that has made like even transformers viable for self-driving cars. Like actually Comma AI uses transformers for how do you call it, for self-driving cars. And the good thing about transformers is that they're one of the first like algorithms to show scaling, like when you scale things up, like how GPT has done. When you scale things up and scale the data to get better results, so they can also really scale well for for the videos that are used in self-driving. So I'd say at this point, like transformers can be used in self-driving, and Comma AI actually uses self-driving for transformers for self-driving. Yes. I think that the question there was about the speed. It was about speed because of the quadratic like expense of transformers. But I think for now it's something that people are doing research about and minimizing that. Like there are more efficient ways of calculating the attention. But with this knowledge, I think you can you can be able to ramp up your understanding of how they do it. I hope that answered the question.
Yeah, sure.
Yeah, perfect.
All right. Yeah, I guess this will be a good place to end. I can't thank you enough, Eric, for like spending time to prepare this and prepare the presentation. I guess all of us are going to learn a lot from it, even those who didn't make it, who will be listening to the recording. So we always upload it to our YouTube channel. So I hope people will gain some stuff from it. And thank you so much. And thank you for folks who made it conspicuously. The one who was popping up was Dr. Sam. Thank you for joining us today.
No worries.
Yeah. So, and everyone, the externals like Tom, and I saw someone else who's not a Microsoft, Alvin, and of course Elton. Thank you so much for staying on and for coming. Have a good day, and we'll catch you next month. We'll also have another interesting paper next month. I'll post it.
Perfect. Thank you so much, Nanda. And thank you everyone for attending. I'll also share the slides with Nanda if that's okay. Yeah, and thank you, Sam, Marisa, for allowing me time to do this. Yeah, thank you everyone. And happy to talk more about vision stuff and transformer stuff.
All right. Thank you so much. Okay.
Bye.